So I'm going to talk a little bit about some quantum circuits for block encoding of sparse matrices. This is joint work with Dan Camps, Ling Ling, and Ru Van Buelman. So let me give you maybe perhaps a little bit of a background of this work. So maybe about a year and a half ago, I was trying to learn quantum computing. I was reading about quantum walks. And I, since I'm more of a practical person, so I try to actually write down circuits for quantum walks. It turns out to be not such an easy thing to write down quantum walks induced by certain classical random walks. So I talked to Ling a little bit, and he told me about the connection between quantum walk and block encoding of stochastic matrices. So we started to look into how to block encode. How to actually write down circuits for general block encoding of general sparse matrices. So basically today I'm going to share with you some of the experience that we had in this type of research. So this talk is organized as follows. So I'm going to start with sort of the classical view of large-scale numerical linear algebra. And this is, for the last maybe 20 or 30 years, this is the area that I worked actively in. And then I talked briefly about quantum algorithms for linear algebra. Particular version of it is this block encoding quantum singular value transformation-based approach, which you have heard of in the last couple of days. I would like to draw some maybe comparison between these two approaches, the classical versus the quantum approach. But then the rest of the talk, I will focus mostly on the practical aspect, which is, how do we actually write down circuit for block encodings of well-structured sparse matrices. And then one particular type of sparse matrices that I will talk about is this classical Markov chain random walk matrices, and how do we actually block encode that to give quantum walk circuit. So let me talk now about sort of the classical view of large-scale linear algebra. So in numerical linear algebra, we typically solve these problems, linear system equations and least squares and eigenvalue problems. When the matrix of interest A is very large but sparse, or when the matrix vector multiplication can be performed very efficiently, we typically, not always, but we typically use iterative method. And all of these iterative methods, essentially, what they do is they construct some kind of polynomial approximations to some functions of interest. For example, in linear system solves, we basically try to construct a polynomial to approximate 1 over x. Least squares basically try to approximate a pseudo-inverse, and eigenvalue, you can think of it as, if you're targeting one eigenvalue, you're trying to basically try to come up with the polynomial approximations of the delta function. So here are some of these polynomials and how they approximate the function of interest. Now, in quantum sparse linear algebra, in this particular approach, so the challenge is that A is generally not unitary. So on a quantum computer, the only operation that you can do is unitary transformation. But for general sparse matrix that's not unitary, it's somewhat difficult to handle that. And then also another difficulty may be that some standard linear algebra operations, such as Axb's and dot products, they're not easy to do. So one way to get around that is to use this block encoding idea, as you've heard about in the last couple of days. So the essential idea is to embed A into a much larger unitary that can be implemented on a quantum computer through some kind of a circuit, which is basically a decomposition. And since ultimately we are going to actually approximate matrix functions or polynomial function of polynomials of A, then in the end, we actually would like to block encode polynomial matrix polynomials. And by using the block encodings of A as the building block. So this is basically, idea of quantum idea of quantum signal processing, quantum singular value transformation. And then once we have such a block encoding, then we apply that unitary to a carefully prepared state and make measurements to get what we want. So this is the approach that has been developed in the last few years, which has been quite successful, at least conceptually. So let me now just try to draw some comparisons between the classical and quantum approach. So to some extent, whether you're doing classical or quantum algorithms for solving linear systems, ultimately, at the theoretical level, we're basically doing polynomial approximation, right? So that's pretty clear. And in terms of the methods, in classical approach, we've developed things like power method, Chebyshev semi-iterative methods, and more recently, Krylov subspace method. And these methods try to use matrix vector multiplications to implicitly essentially construct a matrix polynomial approximation to target function. Whereas in quantum approach, we can't do this directly, but we have to embed these matrices or matrix polynomials into a unitary and through quantum singular value transformation. On the practical side, in classical numerical linear algebra, especially iterative methods, we pay a lot of attention to fast sparse matrix vector multiplication. Right? We use matrix reordering, blocking to make it efficient. And then on the quantum side, in order to make this quantum algorithm efficient, ultimately we have to be able to decompose the block encoding unitary into a circuit that has not too many gates. Right? So that leads to this sort of a complexity issue. So the complexity has two parts. In the classical numerical linear algebra iterative methods, complexity means that we like to use as few iterations as possible. So we like to cut down the number of iterations, and often that depends on the condition number and your target accuracy level. So we spend a lot of time developing preconditioners to try to get the condition number down. And then also we like to get each iteration to be efficient. That means we like to minimize the flops used in performing sparse matrix vector multiplication. We usually like to get it to as close as possible to order n, where n is the dimension of the matrix. Sometimes we may not be able to do that. We get n log n. That's usually considered quite efficient. And in addition to that, we also worry about data movement, memory localities and things like that. Now on the quantum side, there's things that are similar. When we do QSVT, so the degree of polynomial determines essentially the query complexity. So the number of times we have to access the block encoding of the original matrix A. And that also depends on, to some extent, the condition number and error accuracy tolerance. And then we have the gate complexity, which is the number of gates used to implement block encoding. So that's sort of equivalent to the complexity within each iteration in the classical algorithm. And then, of course, more complicated issues like circuit topology, which is more like the data movement locality issue, that's sort of in parallel with the classical work. So in this talk, I'm going to focus mostly on the efficient block encoding circuit, so which is more practical issue. But the practical is still in the sense of sort of fault tolerant computing. So I'm not, targeting NISQ machines. I'm not going to address, things like topology and things like that. And I'm talking about things in the framework of block encoding and the quantum singular value transformation. Okay, so now let's go back to block encoding. So I already mentioned, so the idea is embed A into a unitary, and then we apply that unitary to a set of a sort of extended vector that consists of a set of qubits. Part of it is what's called system qubit that allows us to prepare the input. And then a part of it is ancillar, it's called ancillar qubit. that used to essentially do the block encoding. Okay. Once we apply the unitary to that, you can write it in this form, and by measuring the ancilla qubit, you can actually retrieve or keep the product of A and psi in the system register qubits. So that's pretty clear. But of course, you know, in the end, we like to actually block encode not just A, but polynomial of A. So you can, you know, use this formalism. But of course, the key thing here is that, of course, we don't actually compute the polynomial in A ahead of time. So this has to be done sort of in an implicit form by basically using the block encoding of A to implement the block encoding of polynomial A. And this is done. Fortunately, the theory for that has been developed. So basically, this follows from what's called the quantum eigenvalue or singular value transformation theory that basically says that we can block encode a polynomial A for a large white class of polynomials by basically constructing a circuit in this particular form, which has these phase gates interleave with the block encoding of A, or the inverse of that. So this is an example for a second-degree polynomial. It looks like that. And these phase angles, of course, depends on the polynomial that you're trying to approximate, you're trying to construct, and they can be computed numerically by this, for example, the QSP package that Ling and co-authors have developed. So now the question still remains, how do we actually, so the bottom line is that we have to block encode A, and how do we do that for a sparse matrix? So you can see sort of like, we can start from the very simple case. So if you have a scalar alpha, one way to block encode that is to construct sort of a rotation matrix that looks like that, okay? Or you can construct a symmetric version of that. And you can sort of generalize this idea to matrices, but unfortunately, if you generalize this idea to this, and this is not practical because, you know, that requires you to compute square root of matrices, which requires eigensolver. So to actually be able to block encode, construct block encode for a sparse matrix A, we have to somehow encode the positions of non-zero matrix elements, okay? And then we also have to encode the numerical value of these matrix elements. So how do we do that? So before I get to the sort of give a general recipe for doing that, maybe we'll look at another more practical example, which is a 2x2 matrix. Okay. So if you have a 2x2 matrix like this, where the matrix elements are bounded by 1, then you can construct a block encoding matrix UA in this particular 2x2 block form, where the U alpha block consists of just matrix elements from the original matrix A with some sign flip. And the matrix block U beta just consists of sort of a complementary matrix elements from of A, so and with properly defined sign. So and more importantly, you can actually further prove that you can actually decompose this unitary into a product of simpler unitaries. Each one of them is a canonical product of 2x2 matrices, and these matrices consist of these E1, E2 are nothing but projectors, and then these Hadamars and the NOT gates, and then you can translate this decomposition into a circuit like this. But for a 2x2 matrix, as you can see here, we have used 1, 2, 3, 4, 5 gates, which perhaps is not efficient in the sense that the original matrix dimension is 2, and we're using actually, you know, a larger number of gates than that. And this is partly because the original matrix is a dense matrix. Now, to block encode a sparse matrix, we need to do a couple of things. So one idea is this thing, this block encoding of a scalar is important, is this is actually a building block that allows us to block encode non-zero matrix elements. So we'll be using that to encode the matrix non-zero matrix elements. But we also need to encode the location of non-zero matrix elements. So that means that we need to somehow encode a function we call CLJ, where J is the column index of the matrix, and L represents the Lth non-zero in that particular column. So for any sparse matrix, we can actually write down this function, and then we need to come up with essentially a circuit to encode that. And then we use control operations to perform targeted rotations to encode the numerical value. So, and then we need basically at least one ancilla qubit to encode the rotation, this rotation matrix. And then, but we can't just perform targeted rotation for each non-zero matrix element separately, because that will actually require order n gates. That's not considered efficient. So I forgot to mention is when we do the quantum linear algebra, our goal is actually to come up with algorithms that are exponentially faster than the classical algorithm, which is at best order n with a capital N. So in the quantum algorithm, what we try to achieve is complexity of poly log n with a capital N, or poly n in lowercase n. Okay, so here's the sort of the general structure of this block encoding circuit that can sort of meet the requirement that was stated in the previous slide. So this block encoding matrix UA has a dimension of 2 to the n plus 1 times the dimension of the original matrix. It's applied to a set of qubits with J labeling the system qubits, and n qubits used to essentially encode the non-zero location of the non-zero matrix elements, and one additional qubit, ancilla qubit, used to encode numerical value. Okay, so I'm assuming that this matrix is S sparse, which means that each column has most S non-zero matrix elements, and just to make things easy, I assume that S is a power of 2, okay, 2 to the n. Okay, so this matrix, this circuit consists of several blocks. The DS block is basically a diffusion block that basically is used to account all possible non-zero matrix elements, allows us to index non-zero matrix elements in each column. So it creates a superposition of all these L's, where L goes from 0 to S minus 1, okay? And then we're going to take this superposition, apply this unitary OC, which maps L and J to this function CLJ. So whatever function that you give me, I have to come up with an efficient circuit to do this mapping. How I do that will come up later, okay? And then, and this is followed by another unitary we call OA, which basically allows us to perform control rotations to create non-zero matrix elements at the right place. Okay, so this looks kind of a little weird, but just to verify that this is correct, all you have to do is just to do this calculation to make sure. All this basically says that the ijth element of UA is the ijth element of A, and divided by this factor S, which is the number of non-zeros per column. Okay, so and here's the proof. I'm going to skip this in the interest of time. It's fairly easy to show that this works out fairly well. But there's still the question of how do we actually construct OC and OA, and this is in a number of papers. This is called these are called oracles. Okay, but so in the next few slides, I'd like to just sort of tell you a little bit about actually how these oracles look like for some specific examples. Okay, so the first example that I will show is sort of what we call banded circular matrix. So this is, you can view this as adjacency matrix associated with a directed graph, cyclic graph, where the vertices correspond to the column indices and the edges correspond to the numerical values of the matrix element. So in particular, beta is on the subdiagonal, gamma is on the superdiagonal. Because it's circular, you end up with this matrix elements on the corner. So to construct the OC unitary in the block encoding circuit, which actually is used to encode this function that gives us the non-zero, the index of the non-zero elements, the nth non-zero elements in jth column. And for the circular matrix, this is nothing but this function. You can easily write it down. It's nothing but j plus L minus 1 mod n. Okay. And then basically what we have to do in order to construct the OC unitary is to map J to either J minus 1, J, or J plus 1, depending on the value of L. And that's basically what this says, right? So it turns out that these J minus 1 and J plus 1 and these algebraic operations can be easily represented by this shift permutation, left shift or right shift. And these right shift and left shift, they can be further decomposed as a circuit that consists basically of multi-qubit control knots. Okay, so these can be constructed easily. And then now using that, we can actually construct the OC circuit, the unitary for OC. So you can sort of see how this works. So what we do is we apply an R shift, which maps J to J minus 1 for all L. Okay, it's not controlled by anything. So this is exactly what we need for the superdiagonal, okay, the gamma entry, okay, for L equals to 0. And then for the diagonal, we would like to map J to J itself. So what we do is we apply a L shift to offset the R shift, okay? And if L is 1, so this is a control rotation, and control permutation, okay? And then for L equals 2, we apply L square so that it achieves an overall L shift, okay? And then for L equals 3, we only have 3 non-zero matrix elements in each column. For L equals 3, this is outside of the non-zero band. What we do is we apply R square shift to offset the L square shift. So everything is offset, so nothing happens. Okay, so that's what you do to construct the OC circuit. And to construct the OA circuit, it's sort of similar, in a similar fashion. So we're going to use a slightly different definition of CLJ. And then basically what we do is, depending on the value of L, we're going to apply different rotations. So for circular matrix, it has a feature that the non-zero matrix element doesn't really depend on J. It's actually depends exclusively on L, which sort of a diagonal or subdiagonal band you're at. So when L is 0, if we map L equals 0 to diagonal instead of the subdiagonal, and that what we do is we apply a rotation of theta 1, and with theta defined to be the R cosine alpha minus 1. Alpha is on the diagonal, the matrix elements on the diagonal. And the reason you have to subtract 1 from it requires some explanation, but it's not so difficult to show that you actually have to subtract 1 before you take the R cosine. And then for the subdiagonal and superdiagonal, it's relatively easy. The rotation that you have to apply is basically the R cosine of the matrix value in the original matrix. And that's what the circuit will look like. When L is 0, you apply R theta 1, 1, you R theta 2, theta 3, so on and so forth. Okay. And these OC and OR circuits, they're not unique. So for example, I can leave out the R square permutation for the L equals 3 in OC, but then what I can do is I can add an extra rotation to basically zero out that matrix elements that it's supposed to be 0, but it becomes non-zero because you apply these rotations. Okay, So, and then if you put them together, the complete circuit will look like something like this. Okay, you can sort of see that the number of control rotations and permutations only depend on the number of non-zeros per column. Okay, so this is, we assume it to be, for S sparse matrix, we assume S to be a constant, independent of matrix size. Okay, and then each one of these control circuit can be implemented with polylog and gates. So overall, the gate complexity of this block encoding circuit is polylog n. Okay. So, and then you can say, obviously, I mean, the circular matrix is a very easy matrix. So you can say, okay, so it's just too simple, right? And of course, you can modify this type of circuit to encode, to come up with block encoding circuits for more complicated. For example, if you don't want circulant, you want to remove the circulant constraint and block encode a Toeplitz matrix, for example. All you have to do is to add two sets of control rotations to basically zero out these corner entries. Okay. And of course, you can further modify the circuit to even block to encode non-circular or non-Toeplitz matrices, and you can use circuit like that to essentially to encode matrix elements that are all different on the diagonal, for example, or off diagonal. Okay, so so more difficult question is, given a matrix, how do you actually construct a circuit for arbitrary matrix? How do you construct a circuit? And that's a more difficult question to answer. Okay, let me maybe give you. Here, let me have to watch time. Another example, which is slightly more complicated, and this is a matrix that is adjacency matrix for this extended binary tree. So the binary tree is balanced here, and a balanced matrix, binary tree has 2 to the n minus 1 vertex. To make the problem easier, I just add an extra vertex to make it extended binary. And I constructed this in a way so that the alphas are on the diagonal, so these are associated with the internal vertices. And then the gammas are for the root and the leaves, okay? And then all the edges have a weight of beta. Okay, of course you can make this more complicated, but but this is sort of the basic structure that we have. So again, the position and the values of the non-zero both depends on the row and column indices. And the CJL function here is slightly more complicated. So we can define it as CJL is J if L is 0. So that's just the diagonal element. And it's 2 times J if L is 1. That's just the left child. And it's 2J plus 1 if it's the right child. So that's sort of the indexing label that I'm using. And then this is an undirected graph, and it's a symmetric matrix, so it will also have to encode the parent of each child. So the parent of each child, the index is J over 2. So that's how the CJL function is defined. So you can sort of see that for this particular function, in addition to encoding this addition, we also have to encode multiplication by 2. So it turns out this can be done easily by using a swap gate, a sequence of swap gates. So the OC circuit, the circuit for the OC unitary that encodes the position of the non-zero matrix element looks like the following, right? So we for L equals 0, we don't do anything. L equals 1, then we apply this multiplication by 2, which is represented by this M2 circuit, which consists of basically a bunch of swaps. And then if L is 2, we do 2J plus 1. So we do a multiplication followed by an addition. And then if L is 3, we have to do a division. For division, it's a little bit tricky. We have to use additional ancilla qubit to sort of store the carry and use an Hadamard to make sure that we have a zero cat state popping out from this qubit. Okay. So, and the OA circuit is not too difficult. Basically, you just, depending on what L value you have to apply the appropriate rotation to create appropriate numerical entries, either on the diagonal or off diagonal. So, in this case, for example, if L is 0, you just apply our theta 1 rotation, where theta 1 is our cosine of alpha. And then you do have to treat some special cases for like the leaf case and the root, so that proper numerical values are placed at these entries. So that's why all these different controls are used to create these non-zero elements at the right place. And again, if you put the circuit together, and you'll see that the number of control rotations and the number of control permutation are depends only on the number of non-zeros, S, okay, independent of the matrix dimension. And of course, these each one of these control rotation permutations have to be further decomposed into simpler 1 qubit, 2 qubit gate, and this in general can be done by polynomial and gates. Okay, so let me just sort of summarize a little bit. So the general strategy that we use to construct circuit for block encoding sparse matrices is that we construct the OC circuit and OA for non-zero structure, OA for numerical value. And the construction of these two circuit blocks are intertwined. We identify sort of the most general case for to encode this function CJL that can be efficiently implemented by a circuit. But then we have to encode these some edge cases, special cases, hopefully only constant number of them in OA to basically zero out matrix elements where they're supposed to be 0. Okay, and ultimately by doing that, I give 2 examples and show that you can do this in polylog n gates. Okay, now let me just talk. I have about 5 minutes left, I believe, maybe less than that. I'll talk a little bit about a special type of sparse matrix, which is this Markov chain stochastic matrix that we have to block encode. So I choose doubly stochastic because in general you have to work with the discriminant matrix, but just for simplicity, I'm just going to stick with the stochastic matrix itself. And quantum random walk basically power up the matrix and multiply it with the initial probability distribution. A quantum block basically is a block encoding of a Chebyshev polynomial in this matrix. And there's reasons that why this is more efficient, basically related to the eigenvalue gap between the in the original matrix and the polynomial transform matrix. Okay, so so how do we actually block encode the Chebyshev polynomial of P? So the previous techniques that I talked about, they all use block encoding circuit for A divided by S, okay, where S is the number of non-zero in that matrix. Okay, for many applications, this is not a problem. Working with A divided by S is just as good as working with A. But for quantum block, actually, it's a bit tricky. We really need to block encode polynomial, Chebyshev polynomial of P instead of P divided by S. One remedy is that we can always express T of P as a linear combination of Tj P divided by S, but it turns out that this is not efficient. The reason is that to find the QSVT circuit requires this polynomial, which is no longer Chebyshev polynomial in P divided by S, to have magnitude bounded between -1 and 1 on the interval, between -1 over S to +1 over S. In order to achieve that, you have to divide this whole polynomial by a big factor, and that makes the measurement inefficient. Okay. Another way to do that is actually to block encode the P directly instead of P over S. Okay. The circuit, so for doing that, has this structure. So we have to basically construct a unitary transformation that maps the 0 caps to the column, a particular column of this stochastic matrix, taking the square root for each column J. Okay, so this is actually where the complexity is, and then if you can do that, then you can successfully construct a circuit that looks like this. Okay, so it turns out that to construct a circuit to achieve this is not so easy in general, but for problems with special structure, you can do that. So in particular, if the stochastic matrix is a random walk on a cyclic graph, and then you can construct this OP in 2 steps. In the first step, what you do is you map the zero cat to basically the first column of this stochastic matrix after taking square root of each matrix element. And then in the second step, basically you have to construct a circuit that maps basically all these other columns to the first column. This turns out you can do that by basically taking the powers of the L permutation matrix, which can be efficiently decomposed further as something like this. Okay, and I'm going through this a little bit fast, but this is basically what you can do. Okay, and then once you can do that, you can come up with efficient circuit for a quantum walk. Okay, so I don't have time to talk about these other type of the blocking encoding circuit for more general sparsity matrices, the sparse matrices that allows you to encode both the non-zero rows and column indices, and also sometimes you can come up with Hermitian block encodings or Hermitian matrices. They have these structure, but I won't be able to go into the detail. So now let me just conclude. So I talked about block encoding based on linear algebra is practical only if we can actually construct block encoded circuits for the block encoding of the sparse matrices efficiently. Efficient means in polylog n, a number of gates. The decomposition is non-trivial even for well-structured sparse matrices. The composition requires an efficient OC to encode the position of non-zero matrix elements, and an efficient OA to encode all the numerical values through control rotations. And the construction of these unitaries are often closely coupled. Block encoding a random walk requires a slightly different strategy. And there are many other issues that I haven't talked about here that we have to worry about in practice. Okay, thank you very much.